Good morning, ladies and gentlemen. May I have your attention, please? Thank you. Let's go ahead and get started with our translating differential equations from a written description to the mathematical statement using proper calculus notation. So for our Bellwork today, we were asked to translate into the corresponding differential equation. Remember, a differential equation is just an equation that involves one or more derivatives. So let's go ahead and translate. The rate of change in y with respect to x is directly proportional to y itself. This is perhaps the most famous differential equation, and it lends to a famous formula you guys have been working with back since advanced algebra. So the rate of change in y with respect to x, we know that's dy dx, right? There's a rate of change in y with respect to x. And in this case, we're told that that rate of change is directly proportional. So is my verb. So is would be my equals. Directly proportional to, that means k times. So k times. And then y itself, well, that's y again. So dy dx is directly proportional to, that means k times, and then y itself. And so dy dx equals k times y. Raise your hand if you had this. So dy dx equals k times y. Great. So the general solution to this differential equation is a very famous formula that you've already worked with, and we recognize that as our kind of our A-PERT formula, right? Our A-PERT formula, and that shows up in a variety of real-world applications, from carbon dating, radioactive decay, to population growth and compound interest. All right, so we're going to go ahead and solve this one in just a minute, but first let's keep translating, then come back. So let's practice translating. The rate of change in g with respect to t, stop. Let's go ahead and write that with Leibniz notation. So the rate of change in g with respect to t, that would be dg dt, right? dg dt is, there's our verb, directly proportional to means k times, and then this time it's the difference between 100 and g. How are we going to write the difference between 100 and g? Well, we know that difference refers to which operation? Well, that would refer to subtraction. So difference between 100 and g, 100 would come first because order matters for subtraction. So in this case, I would do quantity 100 minus g. Take a look at your number 2 translation and raise your hand if you had this. So do you have the difference 100 minus g? Good job, you guys. If you didn't, go ahead and fix it. We're going to practice translating and solving to find both the particular and general solutions to differential equations today. And today's a big deal. Now, on the AP exam, you're going to have to both find the general and the particular solution that satisfies a given differential equation, for sure. And that's showing up both on the multiple choice and on the free response. It's one of the 6 questions on the majority of the years, the last 5 years. And so we don't know what's going to come this year, but my guess is that, again, one of the free response questions is going to have a differential equation built into it. And so we need to be able to solve separable differential equations, and we're going to practice that today. So it's a big day. Number 3, let's translate. The rate of change in L with respect to M, stop. So what would the rate of change in L with respect to M look like with Leibniz notation? So what would that look like? Joel?
dl over dm.
dl over dm. Awesome, thank you. So there's the rate of change in L with respect to M in Leibniz notation. Is, here's my verb, directly proportional to, that means k times. And in this case, they're saying directly proportional to the sum of L and 4 times M. And so now we've got to translate and work out the order of operations here. The sum of L and 4 times M, right? Depending on how you interpret that, you might get a different result than your partner. Well, it's important to note that sum of would be addition. L and 4 times n, I would group the multiplication, right? The multiplication of 4 times n would occur before the sum because of our order of operations and our hierarchy, right? Please excuse my dear Aunt Sally. And so I would interpret this as sum of L and 4 times m. I would say that would be 4 times m first, then combined with the L. And so this is how I would group it. In any case, we're going to find the general solution to each of these throughout the course of today's notes. We need to be able to do number 1, right? We need to be able to do number 1 for sure at this stage in your life, and then we're going to expand that today. So let's go ahead and go back and find the general solution to the differential equation in number 1. So recall the general solution, right? We want to get an equation, y equals, my dependent variable equals, and then blah, blah, blah in terms of x, my independent variable. And I can see all that from my Leibniz notation. I know that my general solution will be a y equals equation. because y was my dependent variable. It's on top of my likeness notation, and it's going to be in terms of blah, blah, blah x's. Because x is my independent variable, I can see that with my original likeness notation. It's the variable on the bottom, my dy dx. All right, let's go ahead and do that. So what do we need to do? We need to first separate the variables through multiplication or division. So we saw this yesterday with m's and with t's a couple different times. So our first step would be to divide the y over and multiply the dx over. So through multiplication and division, we're going to separate the variables, get all the y's on one side of the equation and all the x's on the other side. So our first step would look like this. We would divide over the y and get dy over y. Then we multiply over the dx and get k dx. So our first step is to separate the variables. We saw that back in step 2 from our money example. Next, we're going to go ahead and integrate both sides. This will be two separate antiderivatives, right? We know on the left-hand side, anytime we have an integral symbol, we have to have a dy or a dx or a dt, right, to tell us what variable will be in our antiderivative function. Let's integrate the left-hand side with respect to y. Let's integrate the right-hand side with respect to x separately, and we'll generate two antiderivatives. So on the left-hand side, recall that a quantity on the bottom to the first power, so long as the derivative of that quantity is separate, will integrate to the natural log function. So we'll do natural log of absolute value of, this is just y, because the derivative of y, right, 1 is present, 1 dy. So let's go ahead and integrate. We get ln of absolute value of y, close bars, plus c. On the right-hand side, we'll go ahead and find an antiderivative for the constant with respect to x. What's an antiderivative for 2 with respect to x? Well, 2x. What's an antiderivative for negative 7/3 with respect to x? Negative 7/3 x. What's an antiderivative for k with respect to x? James? Kx, comma maybe. So kx plus c would be an antiderivative of the right-hand side. Nice job. Now we wanted to solve for what? Well, we wanted to solve for y, to get y as a function of x. We should get a general solution would be a function y equals and blah, blah, blah in terms of x's. So what do we need to do? Well, we've got to isolate, right? We've got to isolate that y. So it looks like we'll subtract over this constant c. We saw last class when we take this plus c, some constant of integration that we don't know, and subtract off another constant of integration that we don't know, we're just going to get, well, a constant that we still don't know. And so if you'd like to be, right, if you'd like to be very descriptive in your labeling, you could call this C sub 1 and then C sub 2 and then C sub 3. I'm going to go ahead and trust that you know combining a constant C that we don't know with another constant C that we don't know is just going to result in some constant C that we still don't know. So I'm going to go ahead and just call this C. So ln y is equal to kx plus c. That's C. All right, now the exciting part. We're trying to get that y alone, and so we know that natural log, right? Natural log is is an exponent that e must be raised to produce the given input. And so when we rewrite this using the definition of natural log, we could say e to the quantity is equal to the input. And so we can get rid of that natural log by rewriting it as e to the. So here we go. E to the kx plus c is equal to the absolute, well, I'm going to go backwards. I'm going to keep the line on the left. So I'm going to say absolute value of y is now equivalent to e to the kx plus c. Plus c. Now we can go ahead and use our properties of exponents to break up this sum in my exponent as a product of two powers with like bases. In this case, the base on this power expression is e. And so I know that just like we took x squared times x to the 7th is x to the 2 plus 7 is x to the 9th. We added exponents when multiplied powers with like base. So too could we break up a sum in the exponent and rewrite that as a product of powers with like bases. In each case, the base will be e. So we'll keep our absolute value of y just for this step and break up this sum as e to the c times e to the kx. So we've broken up that sum in my exponents using properties of exponents and rewritten as a product of powers with like bases, right? E to the c times e to the kx would be e to the kx plus c. All right, now we're going to go ahead and get rid of the absolute value bars. So how will we do that? Well, we know that absolute value bars will return positive or negative depending upon what's in the expression. So to rewrite with this without bars, To drop the absolute value bars, we'll include a positive or negative with our e to the c times e to the kx. And keep in mind that this e to the c is just a constant that we don't know. When multiplied by the positive and negative is still a constant that we don't know. So what we're going to do is group this plus and minus e to the c and call that its own constant, in this case the initial value a, right? So plus or minus e to the c will be now known as our initial value a. We've got y alone on one side, and it's going to be given by a times e to the k times x. Not long ago, you saw a very similar, right? A very similar equation that was a equals p times e to the rt, right? Soon after, you saw another equation, y equals y naught times e to the kt, right? And a variety of different real-world applications abound here. So we've got our continuously compounding interest formula, our APERT formula, affectionately known as. We've got our radioactive decay, right, that we often use with half-life or carbon dating for negative values of K, and so on and so forth. And so just by changing our variables around, we can now use that continuous growth or continuous decay equation. All right, raise your hand if you had it. I can't wait to box this, make it PDFable. You guys got it? So you're going to have to do that, right? Again, you're going to have to do that again. Probably multiple times. All right, so let's go ahead and box our general solution. What kinds of questions do you guys have on today's Bellwork? All right, and let's go ahead and take care of our OTL number 1. Again, that was out of 19. Out of 19. Please give yourself credit for those who completed. You don't need to staple the half sheet, but I would ask that if you have multiple pages that you do staple those together, please. After giving yourself credit for those you complete out of 19, divide, enter, multiply by 2. Please make sure you box into the canvas score nice and big. Round to the nearest half point on top, 0 to 2. Please check with your name first and last. 1A, number 1 are clearly labeled. Before passing it from the front to the back, please keep them in the same column in front rowers. If you make sure they're facing the same direction, I really appreciate your help. Everybody good with number 1? Great. Then let's get going. So, if the rate of change in y with respect to time is directly proportional to the amount y with constant proportionality k, we saw from last closure that a differential equation relating y, t, and k would be given by, now with new variables from today's Bellwork. These are different variables. Go ahead and share with the class what differential equation this would be with y, t, and k. What would that look like? Hayden?
dy dt
Good. In this case, our y was changing with respect to time, and then it was still directly proportional to the amount of y itself. This is the same differential equation as before, just with a different independent variable. Therefore, my general solution, y equals, will not have an x in it. Instead, it will have a t in it, my independent variable. And so my general solution will be given by y equals a initial value times e to the, in this case, k t. Again, that's still my APERT, right? That's still my APERT. And so we're going to run into that several times throughout the course of this unit. All right, today we're going to solve separable differential equations. We're going to solve separable differential equations. In general, you're going to be asked on the AP exam to do 2 things. One, we need to find the general solution to the differential equation. That's what we did in number 1 of our Bellwork today. The general solution still has constants, right, that we don't know, like that constant a, that initial value a. We didn't know what that was. The next thing you're going to have to do is find the particular solution to the differential equation that satisfies the given condition. This is the more specific example where we'll be able to go back and plug in some data point, some piece of information that would allow us to find that unknown constant a, that initial value in the case of that differential equation's general solution, y equals a times e to the kt. we'd be given a piece of information that would allow us to find A. I want you to know that there's a variety of different differential equations, though. They're not all going to be of the form A for their solution, right? So we're going to go ahead and practice finding the solutions to different differential equations, both in general form and particular form. So let's go ahead and get cracking. Let's find the general solution to the differential equation. So this is the rate of change in G with respect to T is directly proportional to the difference between 100 and G. So this is our Bellwork number 2. We're going to go back and we're going to now find its general solution. So again, start with the differential equation, please, and write this notation. Go ahead and share with the class what we had for that. So the rate of change in G with respect to T is directly proportional to the difference between 100 and G. What does that look like with the math statement? Michael?
dg over dt equals k times 100 minus g.
Awesome. In order to solve a differential equation on the AP exam, we're going to have to be able to separate the variables through multiplication or division. If we can't separate the variables, right, then we'll be unable to solve the differential equation in this course. So let's make sure that we can separate the variables. We need to make sure that we get all the dependent variables, in this case G, on one side of the equation, and everything else on the right side of the equation. So let's go ahead and see. Could we do that? Well, yeah. We could divide by quantity, 100 minus G. And we can multiply both sides by dt to separate the variables. So in one fell swoop, we will have gotten all the g's on the left and the t's, the independent variable, on the right. So here we go. That would give us dg over 100 minus g is equal to, and we've gotten rid of that quantity, so we're just left with what? K dt. So we've separated the variables successfully. It's fine that we have 100 here. It's fine that we have some constant k here. But what's important is that through multiplication or division, we've gotten the dependent variables all on one side, and we've gotten the independent variables on the other side, right? We can't have the t's and the g's mixed on the same side, and we don't. So we're good to go. What do we do next? We integrate both sides. On the left, we'll be integrating with respect to g. There's our dg. On the right, we'll be integrating with respect to t. Okay, so what antiderivative rule will we be using overall if I have this quantity on the bottom to the first power? So what antiderivative is a potential rule if I have a quantity on the bottom to the first power? What am I going to be using here? Kobe?
Natural log.
Natural log, right? We can utilize the natural log rule if I have a quantity on the bottom to the first power, so long as the derivative of that quantity exists. And right now, that quantity 100 minus g, the derivative of that with respect to g would be -1. Do you guys see that? It would be -1. And so we can provide a constant multiplier. We can provide that negative. So long as we cancel it out in our antiderivative, we know that we can integrate this rather to opposite of natural log of absolute value of quantity 100 minus g. Let's do it. So we get opposite natural log of absolute value 100 minus g on the left. Close bars plus c. And then on the right, we're going to get the antiderivative of k with respect to t. We saw in the beginning the antiderivative of k with respect to x is kx. So the antiderivative of k with respect to t is going to be kt. Now you'll notice that I didn't write a plus c on the left-hand side. And we did in the very beginning when we were generating the general solution for number 1. From now on, we can include a single constant integration on the right-hand side. And the reason for that is that our constant integration plus c generated on the left antiderivative, when combined with the constant integration on the right antiderivative, is still going to give us a single constant c that we don't know. So from now on, put your plus c on the independent variable side. You don't need to include it on the dependent variable side. And we've seen that now in our activity and again in Bellwork. So once again, you technically generate a constant integration anytime you evaluate an indefinite integral. That is an antiderivative function, but we're going to always now combine those constants of integration as a single c on the right-hand side, the independent variable side. Is that good? Awesome. All right, so what are we trying to solve for in this mess? All right, we're not trying to solve for y this time. What are we trying to solve for? Brandon?
We are trying to solve for. I thought we were solving for G.
We are.
Oh yeah. Oh, you said not solving for Y.
Correct.
I'm a little.
No problem. We're going to find the dependent variable. We need to write the dependent variable y equals, in this case, g equals. So we've got a little bit of work to do. So the first thing we'll do is divide everything by -1 to get the natural log alone. So I'll go ahead and divide everything by -1. And when we do that, notice how right here we would get negative kt minus c, right? We get negative kt minus c. However, this constant c, right, get ready, is some constant c that we don't know, either positive or negative. And so when I divide it by a -1, it's still some constant c that I don't know. I'm going to continue to call it plus c. If that bothers you, you're welcome to call it minus c. Right? You're welcome to call it minus c, but just like we combined our constant on the left with our constant on the right and got some constant c we didn't know, dividing by a positive or negative is going to still leave us with some constant we don't know. So I'm going to go ahead and leave that as plus c. All right, next I'm going to go ahead and exponentiate. That is, to get rid of my absolute value bars, I need to do e to the. So the quantity inside, in this case absolute value 100 minus g, is going to be equivalent to e to the negative kt plus c. And again, we're still trying to solve for g. So I'm going to keep my bars on the absolute value for the left. In the meantime, I'm going to break up that sum in my exponent and rewrite that as a product of powers with like bases as we did in the belt. So let's go ahead and keep our absolute value bars for one more step. 100 minus g, close bars, equals. And we're going to go ahead and group this sum in the exponent as e to the c out front times e to the negative kt. Totally worth it. Oh gosh, totally worth it. I thought it was. It should take a lot longer. All right. So we've gone ahead and isolated my absolute value bars on one side. Now we can get rid of the bars. How do we do that? Take the positive and negative. We know that those absolute value bars could return the same thing, let's see what's inside, or it could return the opposite of what's inside, depending upon if the inside quantity is positive or negative. So we can get rid of the bars by applying positive or negative to the right-hand side, and you guessed it, group it. Group it. So now we're going to go ahead and grab onto that plus or minus e to the c. That's some constant that we don't know, either positive or negative, and we'll call that a. Right? Our initial value. Well, it's not initial value, I would just say. We'll call it a constant. And we'll go ahead and subtract over my 100. And finish it out by dividing everything by a -1 again. So I finally get g equals alone. It looks like I get positive 100 minus a times e to the negative kt. A couple important things to know. This general solution, right, this general solution to the differential equation could have, right, multiple values for a or for k or for both. I want you to know that if we had decided to put a negative c back here when we divided, and if we decided to put a negative c right here when we divide everything by the -1, then right here we just would have had a negative c. Right here we would have had a negative c. Right here we would have had plus or minus e to the negative c, but we still would have called that some constant a, right? And so that wouldn't have mattered if we had decided to call it a negative c. Another thing when we divided that constant k, that plus or minus constant k, when we plug in our initial condition and solve for that, this could be positive or negative. And so I want you to know in the equation, right? In the equation that could affect our results. it would be the same exact equation whether we had a positive versus a negative there. And lastly, notice how this a constant, we don't know what it is. So the fact that this is 100 minus a, right? If this is a positive versus a negative, that'll end up being a plus or a minus in my equation, my final equation, ultimately. And so it's a little bit fuzzy when we're dealing with our positives versus negatives and unknown constants, and that's okay. What's important is that if we're given an initial condition, right, then we're going to pin down exactly what those values of the unknown constants are, and that's where we deal with a particular solution. So this is good for the general for right now. What questions do you have about that first one? Let's do another. So find the general solution to the differential equation. Rate of change in L with respect to M is directly proportional to the sum of L and 4 times M. Jeepers. So now we've got to do our translating. The rate of change in L, dl, with respect to M, dm. There we go. So dl, dm is, there's my verb, directly proportional to is k times the sum of L and 4 times M. This is the sum of L and 4 times M. Here we go. So we've done our translating, and we saw that earlier in Bellwork. Our job is to get the dependent variable, right? The dependent variable on one side of the equal sign and the independent variable on the other side of the equal sign, and we can't have them mixed. And so in this case, L is the dependent variable, M is the independent variable. We can't have L's and M's on the same side. So can we do that through multiplication or division? Well, we could divide over that quantity as we did last example and get L plus 4M on the bottom of my fraction on the left-hand side and multiply my dm over. The problem is that I'd still have L's and M's mixed together on the same side if I were to do that. So mathematically I could do this, but it wouldn't separate my variables. It wouldn't allow me to find the general solution. So do you see how this doesn't help us? Right? Do you see how this doesn't help us? So that's not good. What else can we do? Well, can we try distributing through to get rid of the parentheses? Right? We could distribute through and rewrite as dl dm equals kl plus 4km. Is that right? Yes? Awesome. Then we could... Oh, that's still going to have dm. We can't separate here because we have to use subtraction in order to separate, and that's going to make this, right, dm, then apply to both this term and this term when I multiply it to both sides. And so this isn't going to help us either. If we subtract it over that kl, we still have a dm here, and then when I go to multiply that dm over, it'll be multiplying the minus kl too, and so I'd have still m's and l's mixed together on the same side. So this doesn't help us either. So this is an example of a non-separable differential equation, and you won't have to solve that type on the AP Calculus AB exam. So we can't separate through multiplication or division. This means stop. So we can't separate the variables through multiplication or division. Then we can't solve it through separation of variables. And we can stop. We're not able to solve this through separation of variables. In college, if you take differential equations, then you'll learn some other techniques that will allow you to algebraically solve differential equations beyond separation of variables. But in the AP curriculum for AP Calculus AB and Calc 1, you only have to solve separable differential equations. So, who cares? What's the big deal about a general solution to a differential equation? Well, not a lot, right? It's been some algebraic practice. We've done some exponent properties. We've separated the variables. We've done some antiderivatives, right? That's all good stuff. But it's much more useful if we have an initial value, right? An initial value that satisfies that general solution, so we can plug in that data point and pin down what those unknown constants are, that A or that K or both, right? Then we can use it to do stuff like make predictions. Or if it were a mathematical model, right, we could then make inferences using that, solve equations, answer questions that are asked about real life quantities, stuff like that. And so it's much more useful if we have an initial value and can find the particular solution to a differential equation that satisfies the given condition. So let's try some of those. Let's use separation of variables to solve the initial value problem. That just means find the particular solution to the differential equation that satisfies the given condition. So first up, dy dx equals x over y. And we're told that y equals 2 when x equals 1. So let's go ahead and first, right, separate the variables, find a general solution, and then plug in our initial condition, our initial value, and that'll help us figure out then what my unknown constants are. All right, so here we go. dy dx equals x over y. Can we separate those variables through multiplication or division? Well, certainly. It looks like in this case, if we multiply the y over to both sides and multiply the dx to both sides, we would get y's on one side of the equation only, and only x is on the other side of the equation. So this is separable through multiplication and division. I get y dy is equal to x dx. Did you guys get that? Awesome. Next, we'll go ahead and integrate both sides with respect to their corresponding variable. On the left, I'm going to integrate y with respect to y. On the right, I'm going to integrate x with respect to x. These are easy antiderivatives. We need to make sure we include a constant of integration, but from now on, we'll lump those constants of integrations to a single c on the independent variable side, the right-hand side. Let's go ahead and do that. So an antiderivative for y with respect to y would be what? Y squared over 2. And it would be plus c, but we're going to lump that plus c over here on the right-hand side. When I integrate x with respect to x, I get x squared over 2 plus c. I want you to know that as soon as we've integrated, we have the option of plugging in my initial value when y equals 2 and x equals 1 and solving for c. So we do have that option of doing that right now. It's good practice to find the general solution and then plug in last, and sometimes one way is easier than the other, right? Sometimes one way is easier than the other, but it's difficult to tell. I'm going to practice with the general because that handling the constant, right, can be tricky with positive or negative. So I'm going to go ahead and practice with the general solution first and then plug in last. You're welcome to plug in right now, right? And we should get the same thing at the end of the day. And so, does anyone want to plug in right now and solve for C? No? All right, that's fine. So what do we want to solve for here? Well, if Brandon were here, he'd tell us we want to solve for y over there. So we're going to multiply everything by 2, right, to try and solve for y. So our best first step is to times everything by 2. So y squared equals x squared plus, hey now, here's the kicker. C was some constant that we didn't know. When I multiply c by 2, it's still some constant that we don't know. And so I'm going to go ahead and just call this c, right? And it'll be taken care of when we plug in our initial value at the end to figure out what c is. I wanted to solve for y, and so if y squared equals blah, then y must be given by the positive and negative square root of blah. In this case, blah was x squared plus c. And now, right, I solve for y. I found the general solution. We're going to find the particular solution that satisfies the initial condition, the given constraint, the data point. We know that y equals 2 when x equals 1. So we're going to go ahead and use that to find the particular solution. However, right now, we don't have a function. We have a relation. See how we have this y equals plus or minus? I want you to think about, right, the top half versus the bottom half. My given data point would fall on which part of this graph, the top part or the bottom part, given that y equals 2 when x equals 1. So we'd be on the top part or the bottom part, Riley? The top. And so we're purposely going to grab this top part. Right? We're going to cancel out that negative. We're purposely going to use the top part to find my particular because we were given this data point. Now, if we were given the negative 2, then we would need this negative branch, and we would have crossed out the positive because the only way to create the negative value there outside the square root is if we kept the negative side. But because our y was 2, right, we don't need this negative side of the branch, we just need the positive side. So let's go ahead and plug in 2 equals positive square root of 1 squared plus c. We plugged in our initial condition. I'm going to plug in 2. So there's our 1, 2 point. Everybody see it? Everybody see it? Now let's solve for c. So 2 equals square root of 1 plus c. Square both sides, and I get 4 equals 1 plus c. And solve for c by subtraction. I subtract 1 over and I get c equals 3. This means that once I had solved for y and got the general solution, I plugged in my initial condition, my initial value. I solved for c. I can now rewrite this red arrow one with the value of c that I found, 3. So now I need to go back and write the function that we nailed down now. There's no general solution. We found the particular solution, y equals. What is it? It's y equals the positive square root of x squared, what? Plus 3. We nailed it down. Is that a function? Yes. Does it have any other constants floating around that we don't know? No. We've nailed it down, and this is our particular solution. Hooray! We're done. It's pretty sweet. Okay. Now I want to go right back here. After we had integrated both sides, right? That's our first place that we would have been allowed to, find our value of c. If we had chosen, we could have plugged in 1 right here for x and 2 right here for y. Okay? So quickly, I just want to show how we would have gotten the same thing. Ready? What goes in for y? 2 goes in for y. So 2 squared is 4 halves equals 1 squared over 1 is 1 half plus c. So 2 equals 1 half plus c. And 1 1/2 or 3 halves equals c. Uh-oh. What's going on? I thought we determined that c equals 3. Did we do something wrong here? Well, we plugged in right here in this form, y squared over 2 plus x squared over 2 equals c. We determined this constant right here before we had done any algebraic manipulation to solve for y. Here, we would still need to plug in 3 halves right here, right, and do algebraic manipulation to solve for y, so that in each case we get a formula, y equals, right, for our particular solution. So let's take this and plug it in right here for c. I get y squared over 2 equals x squared over 2 plus 3 halves. What's the first thing I do to solve for y? Times everything right here. So I get y squared equals x squared plus 3. And do we see now that we're going to generate the exact same thing? Once I go ahead and solve this for y, I get y equals the positive and negative square root of x squared plus 3. And my data point, 1 comma 2, was on which half? Top half. So we purposely strike that out. And in each case, we generate the same particular solution. Y equals the square root of x squared plus 3. So, moral of the story, doesn't matter where you plug in your given condition, your data point, to solve for the constant. No, you'll get different values of c in the middle, right? If you do it first, you'll have to plug that c back in and then still solve for y. If you do it last, you've already solved for y and you only have to plug it in and rewrite. And so sometimes one is easier, right, than the other. I kind of like to go and find the general solution first and then plug in and just rewrite, as opposed to having to then go back and solve again. But either way is correct. And look, we got the same exact thing. Let's try another. Please use separation variables to solve the initial value problem. dy dt equals y over t. And we know that y equals 2 when t equals 2. All right. So can I separate the variables through multiplication and division? If I can't, then we're not able to solve it. Right? So does it look like we can separate the variables through multiplication and division? Boy howdy, if we divide both sides by y and multiply both sides by dt, we will have separated the variables. And so again, we'll divide by y. On the left, we'll get dy over y. On the right, we'll multiply the dt over and get dt over t. So this was a separable differential equation. We could separate the variables by multiplication and division. Now we can proceed with our integration. On the left-hand side, the antiderivative for dy over y, we know and love, I might add, as ln of absolute value of y plus c. However, we'll neglect to include the plus c here, knowing that we'll group it with the independent variables constant integration over on the right. An antiderivative for dt over t, natural log absolute value of t, closed bars, plus c. All right, let's keep going and solve for y, and then I'm going to plug in at the end. If you want to plug in right now, you may, and compare. At the end, I'm going to go ahead and continue on. So it's good practice here working with our natural logs and our absolute values and our constants. So I'm going to go ahead and do e to the, so absolute value of y is equivalent to e to the natural log of absolute value of t, closed bars, plus c. I'm going to regroup that sum. Absolute value of y is equal to, and I'm going to break that up as e to the c times e to the natural log absolute value of t. I'm going to go ahead and undo the bars now. Absolute value bars would return the same thing if the quantity inside is positive. It'll return the opposite thing if the quantity inside is negative. E to the c times e to the natural log absolute value of t. And now you guessed it. Look at that pesky bugger. Plus and minus e to the c is some constant we don't know. What can we call it? Well, this is cumbersome. Let's call it some constant a that we don't know. Y equals a times, and then e to the natural log of absolute value of t is equivalent to what? Absolute value of t. E to the natural log of something is equivalent to the something. In the same way that the natural log of e to the blah is just blah. So they undo one another due to inverse properties of exponentials and logarithms of the same base. Therefore, this right-hand side is just a times absolute value of t. We've solved for y and generated a general solution to this differential equation. Now let's use my given data point to determine this unknown constant a. So when t equals 2, y equals 2. So we can plug this in. So 2 equals a times the absolute value of 2, which is 2. So 2 equals 2a. So a equals 1. Is that what you guys are getting? So my particular solution that satisfies the differential equation is, right here, I got to go and rewrite this. Y equals 1 times absolute value of t, or simply y equals absolute value of t. What? Y equals the absolute value of t satisfies that differential equation. It means the rate of change in y with respect to t is given by the quotient of the y coordinate over the x coordinate anywhere I look. If I were to consider the graph of this, right, y equals absolute value of t, what would this look like visually? Absolute value of t looks like, isn't that our v? Isn't that our v with vertex blades, not something, blades, right? So that's the absolute value v, whose vertex is at the origin. Let's consider the instantaneous rate of change of this graph, right? If I look at a different point. So what point is this? Let's say this point is 3, 3. What's the slope, right? What's the slope of the absolute value function at x equals, or at t equals 3? Well, it should be 1. Let's go ahead and plug that into my differential equation. The point 3, 3 would be 3 over 3. What's that slope? 1. My differential equation tells me the slope of my function y anywhere along it. Let's pick a different point. Let's pick negative 3, 3. Yes? What's the slope here graphically? What's the slope over here? Negative 1. Now let's check in our differential equation. If I plug in negative 3 for t and 3 for y, I get 3 over negative 3, which reduces to negative 1. The slope of my graph at the point negative 3, comma 3. And so this differential equation has the same meaning that it did back in Unit 3 when we connected the slope, the instantaneous rate of change, right, of the graph is the first derivative of the equation with respect to x. Well, in this, it's still the same thing, but now we're algebraically going back and forth between a differential equation and its particular solution. That's pretty sweet. All right, let's do another one that's more complicated. What? Well, that was pretty easy, don't you think? Let's do one that's a little bit trickier. So let's use separation of variables to solve the initial value problem. Recall we need to be able to separate the variables, that's the independent variable on one side, the dependent variable on the other side, through multiplication or division, otherwise we're not able to solve it at this stage. So dw dr is given by e to the r minus w. We're also told that the initial condition w equals 2 when r equals 0. All right, can we isolate w's on one side and r's on the other side? Well, we have that darn subtraction there. And that caused problems for us before when we were dealing with the sum, right, of the L and the 4 times M. We couldn't separate that through multiplication or division. Does anybody see a way that we could use multiplication or division to separate this? Colin?
E to the R over E to the W.
Nice! We get last class period when we had to do the 2 different conditions with our 2,500 after 3 days and our 6,000, right, or 5,000 after 5 days, and we wrote 2 separate things and then did the proportion. We could subtract top exponent minus bottom exponent. Nice job, Colin. So let's go ahead and rewrite the right-hand side. Again, we're not separating in this step. We're just rewriting in a form that we'll be able to separate by using our properties of exponents. I'm going to rewrite that e to the r minus w as a quotient of powers with like bases, because my shortcut operation was top exponent minus bottom exponent. So this can be rewritten as a fraction. Top would be e to the r over bottom would be e to the w. Nice job. Weren't you on my team, Colin? Now we'll go ahead and use multiplication or division to separate the variables. So I'm going to multiply the e to the w over, and I'm going to multiply the dr over, and I get e to the w dw is equal to e to the r dr. Dependent variable on one side, independent variable on the other side. We did it with multiplication and division. We're ready to go. Let's integrate both sides, you guys. So on the left-hand side, we need an antiderivative for e to the w with respect to w. On the right-hand side, we need an antiderivative for e to the r with respect to r. What? Well, I'm fresh out of rules. Right? What's an antiderivative for e to the w? Do we have a rule for that? Do we have an antiderivative for e to the w? Heavy?
Would it just be e to the w?
Absolutely. The reason we purposely choose to work with natural logs and exponentials base e whenever possible is because their derivatives are cyclical. And the antiderivative for e to the w with respect to w is e to the w. Remember our exponential function, e to the x differentiates to itself, e to the x. And so it makes sense that e to the w differentiates to e to the w. Good, thank you. Heavy, I'd also like you on my team. So far. Plus c, but we're not going to include the plus c on the left, we're going to include it on the right. E to the r is an antiderivative for e to the r with respect to r plus c. What are we trying to solve for? How about that? How are we going to solve for w? Well, remember, it doesn't matter what's over here. We're trying to solve for that. So what I need to do is take the natural log to undo the e. Michael, our team's growing. So we'll go ahead and do natural log of both sides. So natural log of. Do I need bars here? No, we're not using natural log as an antiderivative. Right? That's when we need to include bars to preserve the domain of the original function. Here we're taking the natural log of both sides. We're taking the natural log of both sides as a means for solving for y. So algebraically, we just start taking the natural log of both sides. However, we do have a quantity on the right, that is e to the r plus c, all in the input. What is ln of e to the w? Why are we taking the natural log of both sides? Because natural log undoes exponential base e, and so I just get w. Yay! I feel my general solution is very close. And so it looks like my general solution, w is given by, can't break that up. I can break up a log of a product, but not into a sum of individual logs, but not the log of a sum. It doesn't go backwards like that. So we're going to go ahead and leave this as natural log of e to the r plus c. Here's my general solution. That's on the recording, so you know. You go to 4905 if you want to hear that again. So what are we going to do now? Let's plug in our given constraint. We know that w equals 2 when r equals 0. So we're going to go ahead and plug in 2 for w. And we're going to plug in 0 for r. Therefore, 2 must equal the natural log of, what is this? E to 0 is 1 plus c, so 1 plus c. And I want to solve for c. Variety of properties we get to review during this problem. This is pretty sweet. How am I going to get at that input here so I can see what c is? What do I need to do now? I'm going to go back and do e to the again to get rid of my natural log. So I've got to go e to the second is equal to input 1 plus c. So I have e squared equals 1 plus c. So at the end of the day, when the dust is settled, I get c equals e squared minus 1. But I'm not done. I must rewrite. That's this step right here. I figured out what c is. C equals e squared minus 1. So I now need to rewrite my w. My final particular solution is w equals natural log of e to the r plus e squared minus 1. So w equals natural log of e to the r plus e squared minus 1. Are we have any floating constants around? No. R is our independent variable. W is our dependent variable. This is just like a function y equals f of x. Here it's just w equals f of r. So we're good. We don't have any k's or a's or c's floating around. We found the particular solution. That's pretty sweet. One to go, and then I think I'm going to have to break the news to you. We had a bit of a situation last night at the high school. But first, let's finish this one. So let's use separation of variables to solve the initial value problem. dy dx equals x plus y. And we also told that y equals 2 when x equals 4. So let's go ahead and separate the variables through multiplication and division. So if we divided both sides by quantity x plus y, would that separate the variables? And multiply by dx? No, x's and y's are still on same side together, so that's not going to work. Can we multiply over our dx and get dy alone? No, because then we still have our y over on the right-hand side. If we distribute our dx through, then we still have a dx tacked on, my independent variable, tacked on with the y. And so we still have x's and y's together. And so no, we cannot separate this, right, through multiplication or division. So we can't solve this one by separation of variables. So we can't separate the variables. Again, this is a stop. Because we can't separate the variables through multiplication or division. All right, I want you to know some stuff went down last night, all right? Some stuff went down last night in the staff lounge, the teacher's lounge, okay? And you guys are first on the scene. So you are forensics unit from CSI Wanakee. And you're going to determine the time of death of a staff member. Yes, that's right, Al Jabra, our substitute math teacher, was working late, and this morning the custodial staff found him in the teacher's lounge deceased. Your job as a forensics unit is to determine the time of death, and you're going to do so using Newton's law of cooling, which, incidentally, is the general solution to a differential equation, where the rate of change in the temperature of an object is directly proportional to the difference between the object's initial temperature and the ambient temperature, the temperature of the environment. So when you think back to Thanksgiving, if I can relate every example to food, I will. We open up the oven, right? It is 350 degrees. You take that with the hot pads, of course, your UV gloves, and you put that on top of the stove, so it starts out at 350 degrees, the rate of change in that turkey's temperature, right, with respect to time, is directly proportional to the difference between the initial value of the turkey's temp and the ambient temperature. So if it's a balmy 72 degrees in your house at Thanksgiving, the difference between 350 and 72, right, that difference is going to determine how quickly now that the turkey is going to cool. So initially, that's a big difference. So the turkey is going to cool quickly. However, as that turkey's temperature gets closer to the ambient temperature, 72 degrees, the rate of change in the turkey's temperature is going to slow down. Now, when it's down at 200 degrees, that's less of a difference. Yes? It's not going to be cooling as quickly compared to in the beginning when the difference was greater. As the turkey cools to 150 degrees, now that's less of a difference than 72. It's going to cool more slowly and so on and so forth. And so it's the same thing when you take out something from the refrigerator or put it in, right? And so when you put something in the refrigerator, right, initially its temperature drops quickly, but over time, the rate of change in that object temperature as it sits there in the fridge cooling slows down, right, until it eventually gets closer and closer to whatever your fridge is set up. Okay, so that's Newton's law of cooling. And our bear won't play because of the recording. Together, you and your cooperative learning group, as a CSI Wanakee forensics unit, are going to determine the time of death, and you need to show me that time at the end, and then you'll get your stamp. We'll come together for closure at about 35, regardless of where you guys are, and I'll pause the recording until then. All right, thanks for. So, would like a written response for what does separation of variables refer to? So, what does separation of variables refer to? Each time an indefinite interval is evaluated, a constant integration plus c is produced. So, why is it okay to only put plus c on one side of the equation? Number 3, which side of the equation should the plus c be placed on? And lastly, how does one find the particular solution to a differential equation? Please be ready to share your written responses with the whole class. Okay, go ahead and share your response to the class, please, when I call on you. What does separation of variables refer to? Right? What does that refer to in differential equations? Grace?
Putting like the dependent and independent variables on opposite sides of the equation.
Absolutely. So we want to move the independent variable on one side of the equal sign and the dependent variable on the other side of the equal sign. So good. So I'm placing the dependent and independent variables on opposite sides of the equation. keep in mind that we can only do that using which two operations? Right? We can only separate the variables using which two operations? Sophia?
Multiplying or dividing.
Absolutely. So we're only allowed to do that by multiplication or division. Nice. So each time we evaluate an indefinite interval, we get a plus c. Why is it okay to only include a plus c on one side? Why is that okay to only include a plus c on one side? How?
Because it's unknown, so unknown minus unknown is still unknown.
Absolutely. So combining two unknown constants still results in an unknown constant. Thank you. Which side will put that plus c on then, right, from now on ever after? Hayden?
Independence.
Good, we'll put it on the independent variable side. And lastly, how does one find the particular solution to a differential equation? What do we have to do, right, that is different from Bellwork? How do we find the particular solution? Courtney?
I said you find the general solution and plug in numbers and solve.
Absolutely. You plug in your given condition into your general solution and solve. So plug in your given condition into equation and solve for C or A or whatever. Great job today, you guys. I'm going to go ahead and stop the recording and post it.